Ta-da! I'm here. Okay, so we are covering homework number 7. Here's the solution, and let's go. All right, so here's problem 1. We have these 20 samples of an axial force and a 20 samples of strength, yield strength, taken totally different times, totally different groups of people who gathered this data for us. And we know that both of the load and the material properties are consistent with a normal distribution. We want to find the probability that a strength in the next batch is less than 40 megapascals. We want to find the design factor and required diameter of the rod to achieve 99% reliability. And then we want to do the same, but now with 99.9% reliability. But now we want to go backwards in part D and take a look using that safety factor and we want to find the safety factor and associated reliability. If we use the preferred size from answer B, we're going to get some odd number. And now we want to pick the next size up. So now we want to find what the safety factor is if based on that actual design. And we want to answer the reliability with 4 sig figs. Okay. So here's the data, and what we would do first, right, as part of this, is probably go into Excel and grab a hold of the data, right? And if I was going to cheat here, let's see, not cheat, but let's see, I come up into assignments and I'd open up the assignment 7, and let's see if I can grab these. Oh, is it going to let me do it? I don't know. I'm not 100% sure. I wasn't sure if this would actually work, but this is what I would do if I were you. It might work. Okay, so what we could do is we could sort. We could sort by columns, text into columns, and then we want to. We could go fixed space. That might work. I think we have to turn it into numbers. We might have a problem. Yeah, I think they are numbers. We might have a hard time. Sometimes they'll turn if the spaces into text, or just turn it into something else that it doesn't process, but we have to be aware of that. Okay, so we've just cheated, and we'll get the average. So let's see. Go equal average, boom, grab all of these, and it worked. We can get the average of both of those, so that's the mean, and we might want to get another decimal place right in there. Maybe get a couple, but at least say 4 sig figs. And then go stand dev dot, and we're going to do S, which is based on a sample. And take all of those, and I think there we go, standard deviation, and here. Okay, so let's see, I think, let me see, go back to this, and did I get the same ones right here? Yeah. I don't know, actually the standard deviation, it looks like I might have got something different there for some reason. Interesting. I might have made a mistake somewhere along the way. But I'm going to stick with what I have right here. I wonder if maybe if I change this to P. Did I accidentally have P in there? No, it's you can see how it's slightly different, right? There you go. And this one is slightly different as well. I get the same average, but not the same standard deviation. I wonder why that is. Huh. No, I didn't do the P, I did the S. So my values are going to be slightly off. Why is this? You know why? I think I only did 1/2 of the column. That's my mistake here. So I should try to change all of my values. So all of my values are going to be a little wrong, I think. No, wait, let me go back over this. Let me go back to these. No. I have my 2.64. I got this. Oh no, I got the standard deviation correct right here. 14.65, 14.64. No, that's the average. And I got the averages correct. It's these that are wrong, and I want to check them. Stand dev from right there, and I got 18. Why am I getting something so much different? Oh, the values. I don't get it. Why? Let me double check this. I'm going to paste this in here as values, and they should all be pretty close. We'll do this right here. Boom, I get the same thing. But then over here, for whatever reason, I'm getting, here's my average, here's my standard deviation, and all those values are the same, and I'm getting something different. Stand dev. And this is STDV. Oh, that's strange. Why am I getting something different? I don't know what I'm doing wrong here. Here's my standard deviation of this right there. All of those values look to be the same, and it's giving me 1,887.5 here, and it's giving me 1,839 right here. And I can't figure out why. It's giving me the same value here, but not from here. Wow, that's a mystery. What could I be doing wrong? Because I just copied all of these values right here and pasted them right here, and I'm getting a different value. Okay, well, we got to continue anyway. All right, so here's the averages and the standard deviations. And I want to transform this first part. All right, so in part A here, we were asking for the probability that it's less than 400, right? So right here, we take 400 and subtract out the average and then divide by the standard deviation. And here is the Z transform that we would use. And we would go to table A10 to find this, right? So that's 0.964. So we would take 0.9 right here, and then we would find 6. So it's going to be somewhere between right here. No, there it is. 0.1685 and 0.1660, right? So we would interpolate in between those, or what we could do is we could look up, like we could take this 400 maybe as our variable here, and maybe want to stick this up into here, right? And then we'll find the Z that's going to be accompanying that. So we say equals, and we'll subtract 400, this minus the mean, right, which is that, and divide by the standard deviation, and there's your Z right there. So that's quite a substantial difference from mine. My Z was 0.964, and theirs is 0.99272. So I don't know what's going on. I have it's a little strange to me that my standard deviation is so far off, and I really would like to know why it's so far off. Okay, so anyway, I can look up this in the table, but or I can find what my I don't even want to come up with the iota of the phi for the thing, but this is not turning out to be a very good one here. But we want to find the probability. What we type is equals norm dot s dot dist, and we get this value and then set true, and you get 16.4. So what you want to do, what we pretty much have right here is that's going to be 16.4 0.04%, right? So, but running through it with the values that I got 16.6 right there, right? If I interpolated in between those two. And once again, I don't know why my standard deviation is being different right here. It's still showing that on my other spreadsheet right here, right? So I had my 400 minus 416 divided by that 17, which was the standard deviation of this column worth of data, which should have been the same as this column of data right here, right? I'll paste values next to it, and yeah, sure enough, see, I'm getting a different value right here than I am from this, and I don't know why. What am I doing differently? stdev.s, and that value from there. There. Anyway, let's continue. So now here's my okay, so here's my interpolation, and I get 0.1674, right? 0.1674 is what I got by way of interpolation. So I said there's 16.74% chance that the next sample is below 400, right? So then I go to part B in this, and what I want to do is use the equation. It's in chapter 1, and it is equation, at least in this version of the book, if I can get to flipping through there, I don't see it right off. Okay, so let's switch over to the camera here. We have this equation right here, right? So I want to get this covariance, right? So the coefficient of covariance right in there, and then divide it through. So here is with the values I had. Don't know why they're different. Here is the stress coefficient of variance and the strength coefficient of variance. And then for 99% reliability, I look up in the back of table 810. So table 810 is actually a 2-page table. So we go to the second page right here, and we see for 99% we get that Z of 2.326, right? So and the positive and negative doesn't matter there. So 2.236. So we go ahead and plug this into that equation right in there, mindful of the plus and minus. It's going to definitely be a number that's greater than 1. So here's the design factor that we would use, right? So using that the allowable stress, therefore, with that design factor is 318, right? So we notice we use the average strength right in there. So the allowable diameter, therefore, turning this equation backwards so we could solve for the diameter, we find that we get 7.876 millimeters. Doing the same thing, but this time doing it for 99.9% reliability, which is this guy right here, right? And we get 3.090. So we can plug him in. The coefficient of variance is the same, right? It didn't change. So we find now to increase the reliability from 99% to 99.9%, we end up with a safety factor or design factor 1.417. And I'm keeping more than 2 decimal places, because these are calculation numbers. They're not final answers. So the allowable stress, is the strength divided by that design factor. So now we find if we want 99.9% reliability, we go for 8.192 millimeters, right? And now finally, what we want to do is we're going to take the next size up from part B, which is going to be 8 millimeters. And so we find the stress that's going to be caused by 8 millimeters. We get 308.1. So, 8 millimeters gives us a stress of this. So we can find a safety factor of 1.351, right? So that's how safe we're predicting. Now, if we want to go backwards and predict the reliability, we can take this equation right here, which is also out of Chapter 1, and it's right next to that design factor equation. And it gives us the Z. It's like the thing going backwards. It's right here. There you go. And I'm going to put the safety factor in there instead, right? And if I do that, I get a Z that I have to interpolate. I'm interpolating here, but I could look it up. Therefore, I find that we get 99.57% reliability is what we find from this. And remember, this is only on the material and the load statistical factors. As we discussed before, there are many other things that you would want to consider to cover the uncertainties in a design, not just the variability of loads and the variability of material. But this is something that kind of is a practical application, I think, of using statistics and design factors. So here's 80% reliability, 7.88 millimeters, and then for 99% reliability, we get 8.19. I think I messed that up. That's this right here. I'm sorry, that's a mistake. This should be so that right there should be the 99, which is correctly written right in here, and this should be the 99.9, which is written correctly there. This was a previous problem. I did the 80%, so I didn't fix that. So here's the summary of the thing. And I did say to 4 sig figs right here, but notice there's only 2 sig figs, well, not 2 sig figs, 2 decimal places, excuse me. I did 2 decimal places. All right, so here's problem 2. We want to do some stress concentrations, and I wanted 3 different types, right? So this is 1 bar that's got all these different things in it, and it's 2 inches wide, half an inch thick. Is that true? Half an inch thick? Boy, I feel like I made the thing thicker than that. No, it's half an inch thick. Okay. And I said that this hole was 0.75 inches, whereas the radius of a notch right here is 0.375, and then it goes down to a throat right here of 1.25, right? Well, no, this is the throat, 1.25, and then it gets smaller, and then also goes to a throat right here. And then this radii of the fillet is 0.375. They're sufficiently far away from each other that they don't influence one another, and that's Saint Venant's principle that you would, or something very similar to it, that you would be looking at to say, hey, how far do you need to be so they never interfere with each other. But I found that this right here, the configuration I'm showing right here, worked pretty close. And then we put a tensile force of 8,000 pounds onto the thing. We want to find the safety factors on tensile strength at points A, B, and pretty close to C. All right, so Mr. Laziness is going to show you his Excel spreadsheet instead. Here you go. So here's our first. Here's the common information right in here. I guess this is all common information. And then you have this first hole right there. And we're going to look up into a table that's going to be based on D over W, right? So we take the D over W and D over W is 0.375. So you see that it goes right there, 0.375. And I find that I get a KT, as best as I can look at it, of 2.27. Yours might have been, it's pretty close to 2.3, but I I said 2.27. I think that's pretty fair. I don't think, maybe I do have it in this one right here. What I did to get this is to, you see my green right here, my little green dots. That right there is where I read this thing off, right? And then what I did is I created an equation, right? So you see that equation right there? I superimposed this on top of the graph, and I picked out points and then created a fourth order polynomial that fits it pretty well, right? You can kind of see it. And so now I have an equation for this. So somewhere in here, there's that same equation. So if I put in 0.375, it shows, oh, I got 2.28, right? So maybe I think maybe I did do this by hand, but if I were to do this like with maybe additional accuracy, and this right here, 2.28, looks like we might have, that might actually be better. All right, so, but coming back to this, all right, so, but it's, it's a little bit of judgment, really, want to use your pencil thickness and try to find that as close as you possibly can. The area is noteworthy, right, that we want to use. That's going to be for the nominal stress, and that's going to be really the area. It's this area right here. I could draw it right here. Is that and this right here. So that's the nominal area. What you do is you take the width, subtract out the diameter, and multiply by the thickness, and that's the nominal area. And then you divide 8,000 by that nominal area, and we get 12.8 KSI. And then we multiply this factor times that nominal stress, and we get the maximum stress. And then we take the maximums, then we take the strength, the yield strength, and divide by the maximum stress. And so here is our safety factor. We do the same thing for part B, right here, this part, for the notch. And if we compare, here we're using W over D. So the throat area was 1.25, right? We were given that. And then so we get this ratio of W to D of 1.6. It's kind of close to 1.5, so we're going to get close to this point, this line right there. And then we're going to use the notch radius of 0.375. And that 0.375 to D divided by D gives me 0.3, which is right about there. So I get a 0.3, and I come across, and it's really close to 1.8. I tried to make it 1.8, truth be told, but I also tried to mess around with the other one. So this was really kind of the thing that was driving it, is that I wanted to actually get something that landed on the line or close to it. Anyway, doing the similar thing here, noticeably that I also purposely made it so the nominal stresses are the same in all three of them, so you can have kind of a means of comparison. And so you could see now we get 1.84, right? So we get a lower stress here, and we get 1.84 is the safety factor due to that that notch. And then lastly, we have this fillet right here, right, where we reduce from 2 inches down to 1.25. So that's the next thing that we do right here. So we want to have the D over D. That's the phrasing that they use here for the D over D. So that's 2 inches divided by 1.25, and you get like 1.6. And once again, here is a 1.5, so we're just to the side of that. And then we have an R over D, right? So that's the radius, fillet radius of 0.375 divided by a 1.25, and that's also 0.3, very similar to this other one over here, right? And we could see that it pretty much crosses at 1.6. And then so using that with the nominal stress, we get the maximum stress. and then the comparing the maximum stress to the strength, we get a 2.08 safety factor. And now coming up to problem 3, I want you to do this either in SolidWorks simulation or in ANSYS, and to compare, right? To find, and I didn't tell you to do any like mesh refinement, which you could have, but you know, and that's an interesting thing. But I just want you to get the experience of making some comparisons between a hand calculation here, you know, that you can find in the book. And so here's what mine looks like, just only using stress in the x direction. You don't want von Mises necessarily. I don't think they're going to be any different, but so here I actually did it in 3 different mesh refinements. Here's your first one, which is just like the default. I just hit mesh, and then there's the results. You don't have many stress elements through the thickness. Here's with a finer result right here, and then here's with a very dense result. You can see that I'm dense enough that, you know, it's kind of obscuring the color contours, but you could see the kind of a trend here. Well, not really much of a trend. All right, so there's only 3 refinements there. But for this part A there, I got like 5.6% difference, pretty close. I got really close with my second one. And my third one here, it actually got worse than the second one. So that's kind of an interesting thing. One thing that I'm doing, though, is I'm taking the average across the thickness as opposed to just taking a maximum. So that was just a choice that I made in doing the thing. Kind of interesting on this second one here. I start out at the best one and I get worse as I go along. Kind of funny, kind of weird, not expected. I'd monkey around with it some more if I was doing this as part of like, if I was really getting deep into the analysis of the thing of why that might be. I might try a couple others out, see any kind of trends that might come about. And then for the last one, C, I do improve on each one, right? So that's this. And full disclosure, I think I actually picked a spot that was actually closer. And here is my results, and I think probably the one that I have right here at the end, it might be the one. Yeah, it's got that very, very refined. I created a line that was like closer to where the high stress was, and I did refine it down right in there. And if you want to amuse yourself, here's something I enjoy doing. You see here you can animate these and watch it change the pretty colors, right? So, and slow it down so it's nice and. So anyway, that was the results, and I hope you had this was a good experience for using FEA, because I think that's this like really good like introduction to FEA to kind of see the comparison for real things. He did a deflection analysis in homework 6, I want to say, maybe it was 5, and now you did a stress analysis here in homework 7. So we're going to do it with some more things later on. So there you go. This was way too long, 28 minutes. Sorry to be so long.